Now for the last one, let's have a problem that is very, very engineering type problem. So I want you to read the problem first. You may want to pause this video and go back here when you've already understood the problem. Okay? So this problem asks us to find the total cost of fabricating a cylindrical tank. So if you're not quite aware, engineers would love to fabricate materials when they are actually constructed in a customized way, especially when companies would want to store a certain material or a certain fluid inside a tank. So basically, they're fabricating these kind of vessels just to, maximize and optimize the process for each industry. So in this case, we have actually a cylindrical tank. So let's first do this cylindrical tank, and then okay. So this cylindrical tank, this is not actually the color, but I'm just assuming, just to give the lighter shade and the darker shade. So we need to is made up of stainless steel. So this cylindrical tank is made up of stainless steel, and we need to maximize the volume to hold the sludge. So we should be noting that. So we have a volume that needs to be maximized. So this needs to be maximized, and then it will hold a sludge in an aerobic system. So basically, if we talk about aerobic system, because it is very important in this aspect, aerobic system is a system wherein we know that if it is an aerobic system, we know very well that this should be open, because it won't be aerobic if we'll be closing this cylindrical tank. So by this aerobic, we know that it is open at the top. Okay, so this cylinder is open at the top because it's aerobic, but if it's anaerobic, then we know that it should be closed. So the total volume of the scrap stainless steel is 30 cubic centimeter, to be melted and hammered into 0.05-inch thick sheets before fabrication. And so we know that the company will only charge for the fabrication and erection of the total convex area of the tank for 12,000 per meter squared. Okay, so we need to maximize the volume for this, but the restriction presented here is that the total volume of the scrap stainless steel is 30 cubic meter. So the total volume, so we could just say that this is the total volume, and that's 30 cubic meter. So this is to be melted and hammered into 0.05-inch thick sheets before fabrication. So if you have something like stainless steel of a metal craft, so the total volume is 30 cubic meter. So if you will be hammering this into 0.05-inch thick sheet, so for example, this is the sheet, I mean SHEET. So this is the sheet. So let's have something like, let's color it para may gumanda naman ng konti. Let's use this gray. Okay, and then for the other one, so kasi may thickness siya so parang let's have the darker the darker color. So this one. Okay, so kung mapansin nyo, yan yung sheet natin ng metal, and ito syempre connected yan. Yan, connected yan na. Basta metal sheet siya, alam nyo naman siya, hindi siya dalawa, parang isa lang yung sheet. So ito, they hammered it in a way that this is actually the thickness. Ito yung thickness niyan Kung mapapansin nyo dyan, ito yung thickness niya. So yung thickness na yon, that is equal to 0.05 inch. So basically, kung hinammer mo siya sa 0.05 inch thick, what could have been the total area of this this plate or this sheet? So we could just say na if we multiply the width and then the length of this sheet, we could say that that's the area. That's the area of this metal sheet. So that's WL. Now, knowing that this is the area and then that's width times length, we know that the volume is still the area times the thickness, which is also equal to 30 cubic meter. So we know very well that to find this area, we could just take 30 and then divide this by the thickness, which is 0.05, and this will give us the area of our metal sheet. But Before doing that, we know that this is in cubic meters and this one is in terms of inches. So we need to convert that before we perform any operation. So with this, the area is equal to 30 cubic meter. So I'll be adding the units so that you can see it. So that's 0.05 inch, and then so we know very well that for every 1 inch we have 2.54 centimeter. Okay, and then for every 100 centimeter we know that we have 1 meter. So in this case, we've already converted this into its respective unit in meters. So we can solve for that, and then we'll be able to obtain a value that is equal to 23,622.04724 meters squared. So this is the area that we'll be using to find the volume of our cylinder. So basically, we know that the volume of the cylinder is simply pi r squared height. And if we're kind of restricted with the fact that the area should just be this large, we know that that's our constraint in this case. So this is the radius. So let's just label this is the radius. Oops. Do I have to label it? You already know where the radius is. So this is the radius, and this is the height. Okay. So this is the general formula that we need to maximize, but we need to find a relationship wherein h can be represented in terms of r or vice versa. Okay. So to do that, we know we'll be taking that from this area. We already know that to construct a certain anaerobic system or aerobic system or a tank, we know that this is open to air or oxygen. So in this case, and of course this one is closed, because if you'll be putting sludge here, then it will just go out here if you don't close this one. So this is it has a base and it's open at the top. So if we need to find the area or the surface area in that manner, we know that the area of that, or the surface area of this metal that will be constructing from these metal sheets that we have, is that the surface area is simply the dimension of the lateral plus the base. So for the lateral area, we know that that's simply the circumference times the height, and then we add one of the bases. Is it bases? One of the base plates. I don't know. The base, just the base. So that's technically the area of the base, which is simply that we could use pi r squared, but since I'm using d right here, so I think we should be using r, since we just written r here. So I'll be using r from now on. So we have 2 pi r h, so that's basically the circumference and then the height, and then we add the area of the base. So that's typically pi r squared. Now, I just wanted to remind you that if the system is anaerobic, so that's closed, so we'll be having 2 pi r squared right here. So we just have to adhere with the problem. Okay, and now the surface area should be equal to 23,622.04724. Okay, because that's quite a constant value. Now, we don't have any h, we don't have any r, but with this, we already know that we can represent h in terms of r or r in terms of h, which is, depends upon you, which is kind of easier for you to represent. Now, I'll be factoring out the things that I can factor. So we have pi, so we could just write 2, and then we have 2rh, pi r, so we have 2h, and then we add this r. Okay, so that is equal to 23.622.04724, and then we divide both sides by pi r, Okay, so that's pi r, and then this will cancel out. So now we're left with 2h plus r. So 2h plus r is this equivalent. Oops. Okay. So this is actually comma. And now if we need only h, so that's h. So we just have to subtract r from this. So we have pi r and then minus r, and then we divide all of this by 2. So we can just add 2 at the denominator and then 2 right here. So this is our expression of h in terms of r. So that's fairly easy to do. So you just have to use the given that you need. Okay. So going back with this, volume is equal to pi r squared height. So I'll be using another color since we'll start substituting. So v is equal to pi r squared height. And then we know that the height can be represented in terms of this one. So we have v is equal to pi r squared height, and then v is equal to pi r squared, and then the height is this 23,622.04724 over 2 pi r minus r over 2. And then we differentiate. Let me just distribute r first so that it will be easier for us. This pi r squared. So I think we have 23,622.04724, and then pi will be cancelled out, and we're left with r here, and then that's over 2. And then this one is pi r cubed over 2. Okay, so this is this looks easier now since we don't have to perform product rule anymore. So now that we already have this expression, we can differentiate that with respect to r. So I will have, we could also represent it in terms of this. So that is equal to, this one is a constant, so we can just divide that. So we have 11811.02362, and we have the derivative of r is simply 1. So we're left out with this constant, and then we have minus we got 3 halves and then pi r squared. Okay, so setting this equal to 0, we know that we can obtain two values based on this r squared. So we have r is equal to positive or negative. So this expression, I'll be writing that on the calculator just to get the value. It's just using shift solve, but you can also manually solve for this. But I'll be getting positive or negative 50.06377. Let's just round it up. So 50.06373. You could just cut it off for 4 decimal places. Okay, so the unit is in meter. So that's it, and that's a pretty large tank for a 50-meter cylindrical tank. That's a very huge tank. It's like a dam. Okay, so but of course we have just to solve for this problem. We don't mind any value if it's even possible. Okay, so the next thing that we have to do is to select which is the correct answer, and for this, of course, the answer should be the positive one, so we'll be only considering the positive value. Okay, so that's our radius, and the question is the total cost of fabricating the cylindrical tank, and it says here that the company will only charge for the fabrication and erection of the total convex area of the tank for 1,200 per meter squared. So the total cost will be coming from the fabrication and erection of the total convex. Okay, so if the cost is equal to 12,000 per meter squared, and this is only applicable for the convex area, so that will be the one that will be needing for, so that will be the money that is needed by the company to have this tank constructed. So why is that so? Maybe because the company didn't charge for the base, because the base is not actually really a problem when you're erecting something, because if you have a plate, something like this, now you have a plate and then you just have to like draw a circle right there, and then that's typically the base. But if we're fabricating the cylindrical tank, then we have to like curve the remaining area just to fit in with a circle. So that's why the company will only be charging for the erection of the convex area in this case. So anyway, it's not our problem. So we need to find the total convex area, and then we multiply that with 12,000, so that will probably be the cost of this fabrication. So the convex area will be coming from this 2 pi RH, because this one is the convex, that this is the convex and this is the base. So again, a convex area is an area that gives you a convex figure. So any figure that will give you a non-concave shape, then that will give you, of course, a convex shape. So convex figures are like this. Okay, they are something like protruding on the surface, and a concave is something like this. So if you have a curve and then you would be something like striking a certain arrow, that arrow would come in on the inside of that figure. But if you'd be striking from the outside an arrow, then you could see that that's protruding, and then the arrow would just it won't go inside. It's something like that. That's the easiest way you can visualize a convex or concave shape, especially in solid figures. So anyway, so we'll be considering only this concave shape, which is 2 pi RH. So with that, the surface area is equal to 2 pi RH. So this is the surface area for fabrication. Let's just use to be constructed with a cost. Okay, so the surface area is 2 pi RH, and that is equal to 2 pi and then times 50.06373, and then we have the height. So actually we don't have the height yet here, but we can just compute for that. So the height is equal to, based on this expression, I'll be substituting 50 from this expression, so you could just do that in your calculator. So the height is 50.063 okay, so as you can see from this expression, they are very close to each other, almost the same, no? So basically, if you were be constructing something like this in the future, you could see that the height and the radius would just be equal to each other, and in that way it will maximize the surface area, but it would of course require some huge amount of surface area. So by the way, that's 50.0636, and then the surface area in this case is equal to 15,748.0090, and the unit is in meters squared. So we know that the cost is 12,000 per meter squared, so the cost of construction is equal to 15,748.0090 times 12,000, because that's 12,000 per meter squared. So the cost, let's use red, so the cost is equal to this is quite a huge number, so I'll be writing 188,976,107.9. that's in pesos. So we have actually 188,976,107.9 million pesos. If you're asking me, this is a very huge amount of money, but Of course, this is just a hypothetical problem. Okay, this could have been lower, but that's just a problem. Okay, so this is the process that we need to do, and you might be noticing that we actually applied something like aerobic system here, just to know that that's open at the top. So there are some quite a number of problems where you will be using concepts in engineering and physics or chemistry. And by the way, this cost something like fabrication, this is actually engineering economics. So those things we'll be applying that in optimization, and we should be having some quite a few readings regarding such cases. But of course, I'll be giving you tips when it comes to problem wherein you will have to apply certain rules or general properties that are actually not that I think will be quite new to you. For example, you'll be using let's say Henry's law or Rawls' law. So I'll be defining those laws first before I'll be introducing the problem, and you can just read it somewhere in the problem itself when I'll be introducing those kind of concept. But for this case, because I didn't actually write something about the aerobic system, because I'll be discussing this on the video. But if this is not included in the video discussion, then probably I'll be adding some note here that the aerobic system would mean that the tank is open at the top, and of course it has a base or something like that. So just to remind you, the capacity of this cylindrical tank is not 30 cubic meter. This 30 cubic meter refers to the volume of the material that has been used in the process of fabricating the cylindrical tank. So if you would be taking the total surface area of this material, you should be getting 23,622, and then you multiply that with the thickness, and the thickness is 0.05 inch. So you should be getting 30 cubic meter. So that's all for optimization. I hope you've learned something from the examples presented, and if you have any questions or any clarifications for these topics, you can just always message me or reach me out. I'm always free to entertain your questions. You can also link some problems if you can find them online, and then you have some confusions regarding the solving on the internet. But in general, there will always be a lot of solutions on the internet, and I wouldn't just like to add to the other solutions. And I would also like to emphasize that I'm trying to create videos that are not on the internet, because that would be redundant, and I just think that the solutions on the internet is also a good option for you to know. So I'll try to always create videos that are not already uploaded on YouTube or other media platforms. Okay, so with that, let's move on to related rates.